First of all, I would like to thank all of you for attending and all of us at Academic Solidarity with Palestine. We're very honored and privileged to be hosting this scientific webinar with Al-Aqsa University in Gaza. So the two of us are organizing it jointly. It goes to show that Al-Aqsa University, like other Gazan universities, have in spite of the incredibly challenging circumstances, have kept on working, and they keep working, and they keep producing the best, and as we can see with Carlo, attracting the best. So we should be thankful to them for giving us this opportunity. So this series of webinars, which starts today with Carlo Rovelli, it'll be a monthly occurrence. Then after Carlo, on 28th of May, we will have Dr. Michel Brouet. Then we will have in June, 23rd of June, Dr. Terence Tao. And we also have a very exciting fall program because we will have Michel Mayer in September, I think, who's a Nobel Prize, Cédric Villani, who's a Fields medalist, and Edward Witten as well. So you see the program is exciting and beautiful. I would like to thank also the University of Lille for lending us its Zoom webinar, and thank the IT team at Al-Aqsa, without which none of this would be possible. So thank you, special thank you. So I will now turn to Carlo. Thank you so much, Carlo, for accepting to do this talk today and to be the first one. It's an immense honor for all of us to have you. Everyone knows Carlo Rovelli, of course, but still, let me say a few words about him. So Carlo is a theoretical physicist. His work has focused on quantum gravity, on the nature of space and time, and on the interpretation of quantum theory. He has also worked on the history and the philosophy of science. Rovelli was born in Italy, but he has worked in the United States, in France, and in Canada. He is a member of the Institut Universitaire de France. He is an honorary professor of the Beijing Normal University. He is an honoris causa laureate of the Universidad de San Martín in Buenos Aires. He is a member of the Académie Internationale de Philosophie des Sciences and is affiliated also to the University of Aix-Marseille in France, as well as to the philosophy department of the Western Ontario University and the Perimeter Institute in Canada. He is also fractal faculty at the Santa Fe Institute for Complexity. Among his awards are the 1996 Xanthopoulos Award and the 2024 Lewis Thomas Prize for Writing About Science. He has written books for the large public, translated into more than 50 languages. In 2019, he promoted the Peace Dividend Initiative, which involved 60 Nobel laureates in asking for worldwide collaborative military expenses reduction. He has been included, incredibly, in the 2019 list of the 100 most influential global thinkers by Foreign Policy magazine, and in the 2021 list of the world's 50 top thinkers by Prospect magazine. So it is incredible to have you today, Carlo. Thanks again for being there. Thanks again to all of you for being here. It's a beautiful sign of the solidarity with Gaza and this academic, intellectual, and of course, more generally, human solidarity with Gazan universities and Gaza in general. So I will now let Carlo speak. He will talk to us about Halfway Through the Woods, the 20th Century Scientific Revolution and its Incompleteness. Carlo, it's you.
Thank you, Anne-Christine, for this introduction. Salam alaikum. You shouldn't thank me. I'm thanking you and all the friends in Gaza, in the occupied territories, for the honor and the privilege of giving this talk and being the first in this series. For me, just let me say one word before starting. For me as a person, the massacres, the oppression, what is going on in Palestine is it's a burden, and I see this as a dark spot in the consciousness of the planet. And living in a West powerful country, which I consider complacent and complice of what is it's going on, it's maddening. I feel powerless. Um, as a scientist, my hope is that in the future, the kind of problems that I'm going to talk about will be solved. And my dream is that a Nobel Prize will be given one day for solving this problem to a young Palestinian woman educated in Gaza and at Gaza University in a free Palestine. I'm going to talk about fundamental physics and open problems, the open problem, what I consider the main open problem in fundamental physics, which is quantum gravity. What I want to do is to illustrate what the problem is, why I think is the central problem around, not the only problem, but a sort of key problem overshadowing the others, and how it might be solved and how the solution might be connected with facts of the world, aspect, phenomena in the world. So I will talk a lot specifically about black holes, which are somehow the great surprise of the last decades from science, the discovery that the universe is full of black holes, and the dark matter, which is another surprise coming from the astronomers who look at the sky, the existence of this strange, mysterious stuff which seems to be out there around the galaxies, and we haven't figured out what it is. So we'll start by saying a few words about the general problem of quantum gravity, its possible solutions, why it's interesting also, why it's fascinating, and then how it connects to black holes, to dark matter, and what the hope of getting out of the darkness, understanding, solving the problem, understanding the aspect of the universe we don't yet understand, and hopefully make some measurement that will, I would say, bring this young woman from Gaza to get a Nobel Prize in the future for having clarified everything. So let me start from the beginning by saying where we are. What do we know about the world sort of at the most basic and fundamental level? Right now, the way I understand it is that in fundamental physics, we have a set of theories which are extraordinarily good and successful, on which the rest is based. And there is a sense, which I'll want to say better, in which we have good reason to believe that all the phenomena that we see in the world follow these theories, respect these theories, and are sort of predicted by these theories. Now, this does not mean that these theories are sufficient for describing nature. They're not, right? Because the world is very complex, and most systems we're interested, biological system, humans, countries, planets, stars, are made by complicated arrangement of stuff, which of course require us specific sciences, specific knowledge, other kind of form of knowledge than theoretical physics. So it's not that theoretical physics explains everything, not at all. However, we have good reason to believe, I think very good reason to believe, that all the other phenomena do not contradict these theories. So in a sense, these theories underpin all the phenomena that we're interested. So even if when we do chemistry or biology, we don't use these theories, we should not use these theories. Nevertheless, in some sense, a biological phenomenon or chemical phenomenon is also a physical phenomenon that is just described by this theories. And what are these theories? Well, essentially there are three. One is quantum theory, which is the general form of mechanics, whatever replaced Newtonian mechanics in the 20th century. The second is general relativity, which is our best understanding of space, time, the structure of space, time, and gravity, the force of gravity. While things fall, the force that keep the Earth spinning around the sun, and the moon around the Earth, and so on. And then we have a so-called standard model of particle physics, which is a sort of a list of material stuff the universe is made of, electrons, quarks, neutrinos, and stuff like that, and fields that give rise to forces between these, like the electromagnetic field, nuclear, other fields that give nuclear forces, and so on. And this, in a sense, we think that to a large extent that is it. This is it. In the sense that we have no phenomenon that clearly escapes that story. Well, there might be something that escapes, but we don't know. We're sure, but nothing obviously escapes these three things. Up to perhaps this dark matter that I mentioned, which we have no idea really how to fit into this set of fundamental theories. What characterizes theories is that all three are recent. They're all sort of 20th century discoveries, and they all came, especially the first two, with a very heavy conceptual revolution attached to them. In other words, when quantum theory was discovered, it was not just a discovery, that there is some new force besides what Newton was or Maxwell thinking, or another kind of equation which people didn't think about. It was really a rethinking of what we mean by matter. Matter is not little stones moving around, but it's a quantum stuff which has very heavy and peculiar phenomena. To understand those phenomena, we need to change our understanding of matter in a substantial way. And when general relativity, which is largely due to Einstein, almost uniquely due to Einstein, or quantum theory is many people that worked on it. It was the same. When Einstein wrote his two theories of relativity, first special relativity and then general relativity, it was not just a correction to the equations of Newton about gravity. It was let's rethink space entirely, let's rethink time entirely, let's understand in a different way what's happening at the same time mean, and let's challenge a number of things that seems obvious to all of us. I will mention one or two later on. So these new physics of the 20th century came as a major revolution, and I think that to another revolution of that kind in our thinking about the world, to find another one has at least to go back to the great the scientific revolution of the Renaissance, the beginning of modern times, the one that goes from Copernicus to Newton, when we rearranged completely our thinking about the world. Before, we thought that it was the Earth with its own science and the heavens, completely different. And then until Newton came about, said, no, it's just one thing. So these major changes of our worldview happens. That's the beauty of science, that makes us change our worldview entirely. And quantum theory, general relativity, and to a lesser extent, the standard model have changed our worldview. Why I'm saying all that and saying, oh, this is great revolution, new ideas, a new way of thinking about matter, space, and time? Well, because it's not over yet, actually. Because, and that's the last line of my slide, if you see the slide here, there is a hole. There is clearly a missing piece of in this set of three theories, because quantum theory is supposed to be the general theory, the general mechanics of everything, and the standard model of particle physics. It's a piece of quantum theory. It's an example of quantum theory. It's a quantum theory. So we understand the quantum features of electrons, of quarks, of electromagnetism, of nuclear forces. Not so for gravity, not so for space and time. What general relativity gives us, it's only the phenomena regarding gravity, space, and time when we can disregard quantum mechanics. Now, very often we can disregard quantum mechanics. When we look at an object, a cup, I was drinking my coffee. Uh, this object has quantum effect. It's a quantum object. I'm going to say something about what are the quantum effects. But usually we don't care about them because they're very teeny, they're very small, they're negligible. To find out these quantum effects that escape our common understanding of matter, we have to go to special situations, very small objects, or a lot of energy, or some peculiar corners of the phenomena, which are very important. I mean, computers are made using quantum effects, lasers are made using quantum effects. The way the sun works is we understand it because of quantum effects. So they're not negligible for the universe, but they're negligible in many of our daily applications. And general relativity is described in this forgetting quantum effects regime, which means that when there are phenomena that gravity is quantum, we expect quantum phenomena also for gravity, just we don't have a theory for it. And examples of these phenomena, there are not many, but we know that in the universe, there are definitely situations in which gravity is quantum. Two are crucial, two are most important. One is the early universe. So we know that we know a lot about the story of the universe in the last sort of 13, 14 billion years. The universe expanded from a very hot and compressed initial state that we called the Big Bang. But we don't know what happened just before. And we don't have the science for for studying what happened just before. More precisely, we don't have a clear established, like all theories, science for studying, because before quantum gravity was crucial. So quantum properties of gravity were crucial. And the other clear case in which quantum phenomena of gravity are relevant are black holes. And that will be a main topic of my what is going to come. I'm going to talk about black holes in a moment. So there may be many things in the universe which are not clear, which are confusing. Aurélien Barraud has a beautiful book, a list of confusing and possibly meaningful lack of knowledge we have about the universe, each of which might be a hint of something new, but there's one which is completely unavoidable, which is these basic theories of science we have do not tell us what happens in black holes or early universe, what happens every time gravity has quantum effects. Now, what are quantum effects? Quantum effects are a number of things. Let me mention two very characteristic. One is discreteness, granularity. Quantum physics is characterized by a quantity, a scale, a constant, which is a Planck scale. At that scale, continuity is broken and things are granular. For instance, light from the sun, light from a lamp. If we ignore quantum effects, we describe it, and we constantly use it when radio waves, lights, all electromagnetic waves are described as continuous waves. Like engineering talk about the waves from an antenna as a continuous thing. But if you look carefully, when the light arrives on a screen, it arrives not continuously. They're just one dot, another dot, another dot, like rain is dotting the screen one dot at a time. And this granularity is like light behaves like it was made by little packets of light, and these are called the photons, the quanta of light. That's the terminology that Einstein was used, quanta of light. So this granularity is typical. All quantum phenomena have this granularity, okay? when atoms were studied, atoms are small enough for quantum mechanics being absolutely crucial and necessary for describing them. They were first understood like a sort of little small planets in which there is a nucleus and the electron going around with some orbits. But then, using quantum mechanics, when quantum mechanics was understood, it was understood that the orbits cannot have any possible energy, only certain energy. So, like energy itself is quantized, so it's only some possible values. That's one characteristic aspect of quantum mechanics. Another one is that you cannot predict the future exactly. The future can only be predicted probabilistically. And systems can sort of jump. This is a famous quantum jumps from which quantum theory started, from one state to the other. So things which are not possible according to non-quantum physics, non-quantum theories, when you look at the quantum aspect, you see that there are these jumps from one state to another, from one solution to another, which are probabilistic, but can always happen. I'll come back to this, to granularity and quantum jump, in talking about black holes. All right. So this was my introduction, what we know, and the big open problem, quantum properties of gravity, we don't know them. But this does not mean that we do not have quantum theories of gravity. We do have quantum theories of gravity. And I've worked all my life with a lot of colleagues, hundreds of colleagues, on what I consider to be the best today attempt to write a quantum theory of gravity, which is called loop quantum gravity. The reason is not a established theory, is that first of all, there are a lot of aspects of the theory which are not clear yet, but more importantly, in science, a theory becomes established when you check it and we test it and you start accumulating confirmed prediction of this theory, right? Science is not about bringing up stories. It's about bringing up stories that give you a prediction, then testing the prediction, and then you start believing the story. That's what makes science science. Now, what is loop quantum gravity? I'm gonna allow me flash one slide with all the equations of loop quantum gravity. I'm not going to discuss any of these equations, but so just you see what it is. It's just a bunch of equations. I'm not going to into that at all, but I'm going to tell you what these equations say. Essentially, what they say is that the granularity of quantum mechanics that, for instance, tell us that the electromagnetic field is made by little quanta of light, photons. It's also true equally for the gravitational field. But the gravitational field, that's a great discovery of Einstein, is the same thing as the space in which we live. That's a major discovery of Albert Einstein. Namely, we have this intuition that we live immersed in a continuous space, but this continuous space is in fact the same entity as the gravitational field. So it's a dynamical field, an electric field or the magnetic field. And as such, it has quantum properties, and it has its own granularity. So we should imagine that if we could look very, very small, the Planck at the quantum scale, this field itself, the space itself, would be granular, meaning we couldn't cut it. We have 5 centimeters, you cut it in half and then in half and then in half. And mathematical spaces, you assume that you can cut forever, can go arbitrarily small. But physics is not necessarily described by the mathematics that we fancy. So physical space, if the theory is correct, once you cut down to the minimum, that's it. So you can think of the elementary quanta of space like little objects which are of minimal volume, minimal size. And these cannot be cut further. These are the smallest entities of space. And then this complicated equation that I flashed for a moment tell you how this evolve or quantum jump from one configuration to another. And it can be shown that in if you disregard quantum phenomena, if you disregard the discreteness because you look at large scale, you get back to Einstein theory, to space and time and gravity as Einstein had described them. But the loop quantum gravity gives you equations for um, describing more, and describing not just the theory that we believe is true and it's been so well confirmed, which is Einstein theory, but also the quantum aspect of gravity. So that is the first part. I just gave you a sense of what is quantum gravity, what is loop quantum gravity, what kind of sort of physics it describes. Now, what I want to do is tell you what we do with that, because as I said, science is not about making beautiful stories. Space is granular and we have beautiful equations. Look how nice they are. Science is about testing whether they tell us something about the world and whether they can predict something that we can measure and confirm the story. And now I want to go to the two phenomena which I mentioned are relevant for all that. And the first one is black holes. So let me say a few things about black holes. Imagine in the audience you've heard about black hole, you know about black holes. Let me say a few things about them. And then a word about dark matter and see what quantum theory tells about that. So black holes, what are black holes? Black holes are something that was predicted by the theory by Einstein. When I was, imagine that in the audience, there are many students in science who are students now. When I was a student in science, I studied black holes. In my book, there was a chapter on black holes, my book on relativity and Einstein theory. But at the time, so I'm not so old, not so long ago, the book was saying, well, this is Einstein theory predicts the possibility of this existence of these things, but more likely they don't really exist in the universe. So it's a theoretical possibility. They were seen as a strange prediction, mathematical prediction of the theory, but it's unlikely that in the universe actually there are those things. Why? Because a black hole, it's something which is has a lot of mass inside a very small sphere. And to give you a sense of what you need to make a black hole, if you wanted to take the mass of the Earth, the planet Earth, and make a black hole with it, you had to squeeze it and make it very small. And you would have to squeeze the entire Earth down to the size of a ping pong ball, a few centimeters. And of course, that seems unlikely that any physical phenomenon in the universe could do that. And that was why, when I studied, it was thought that these things could not happen in the universe, but they do happen. And perhaps the most fantastic discovery about the universe in the last decades is that there are black holes. I mean, here's a picture of them. In fact, there's not just few black holes out in the sky. There are millions, in fact, billions, probably hundreds of billions of black holes out in the sky. They're all over the galaxy, and there are so many galaxies. So there are black holes all over. The universe is full of black holes. And there are some small ones, a big one. This is a picture of one of the biggest. Well, they're even much bigger than that. This is in the center of our galaxy. It's called Sagittarius A star. And the picture was taken with a bunch of telescopes, many of them connected to one another, like these ones. These one are in Chile, I think, in the Atacama Desert, up in the mountains. And using very nice technology, you can get pictured like that. The reason it's a ring like that, we understand it very well, is a bit tricky and complicated. It's a sort of optical phenomena due to the very, very strong gravity around the black hole. Now, why black hole are interesting for the story? Well, first of all, they were predicted by general relativity, and they turn out to be exactly like general relativity predicted. Everything we see about black holes fits with Einstein theory, with general relativity. So in a sense, this is a spectacular confirmation. One more. I mean, general relativity had all sorts of beautiful confirmation. Expansion of universe, gravitational waves. A lot of Nobel Prizes recently were giving to confirming general relativity. And black holes is one further confirmation. Everything we see, it can be fits very well with what general relativity says about black holes. But there are open questions. And here is where we are getting to the point. What the open question? Well, a black hole, it's a hole in the sense that you can imagine as a sphere where you can enter, you can throw stuff in, and you can enter yourself, you can go over it. So the sphere is called the horizon. The surface of the black hole is not a solid, it's not like a star which or a planet. Um, it's just a region that you can enter, and it's called horizon because we don't see beyond it. It's like when you look at the ocean. If you go look at the Mediterranean Sea, you see a line. You don't see beyond that. If you see a boat leaving, at some point disappears. So that line is the horizon because it's the line from which you don't see anything. So the surface of the black hole is similar. It's like a surface such that if something goes in, you don't see it anymore. And the reason you don't see it anymore intuitively is very simple. Gravity is so strong inside that light itself cannot come out. So it's a hole. You can throw things inside. It's black because no light come out. So no light. It's black. And in fact, we see matter falling to black hole. This red ring that you see is not a black hole itself. The black hole itself is sort of in the center where it's blackish, roughly. And this matter is all this red thing. It's all the shining matter that is spiraling around the black hole before falling in, and we can sort of follow the matter toward falling in. So we see, the universe is full of holes and matter falling in, and at this point, every kid can ask the question, "Oh, great! So the matter that falls in, where does it go?" Okay. And with current science, we can say, well, look, we can just trace it. We have the equations. It goes to the horizon, it enters the horizon. We can follow the equations. It falls toward the inside of the black hole. And then we don't know. Because if you follow the matter, when you're inside the black hole, you enter in the region of space and time where quantum effects, quantum gravity effects cannot be disregarded. And that's where you need quantum theory, quantum gravity theory. And that's where you need loop quantum gravity, which is a tentative theory. That's the first open question black hole. There is a second one, which is sort of connected to it, which is the following. If you have a black hole there, plenty of universe there, they keep growing because stuff fall inside and they grow larger. But if nothing falls in and the black hole is isolated, there's good reason to believe, it's a calculation that was done first by Stephen Hawking, that an isolated black hole doesn't stay there forever. Slowly it shrinks, it becomes smaller, smaller, smaller. People say it evaporates by emitting radiation like heat or light very, very slowly and becomes smaller, 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 smaller until it becomes extremely small. And then, well, once again, we don't know. Because what happened at the end of the evaporation, it's really a quantum gravitational phenomenon. We need quantum gravity. So let's let me say what the theory of quantum gravity suggests it's going to happen. And for this, let me say something a little bit more about the inside of black hole, because the inside of black hole is a very fascinating thing. There are these fairy tales in which two kids go in the forest and they see a little hat, and they go in the hat, and the hat is little from the outside, but when they go in the door, is huge inside. Well, that's exactly how a black hole is. There's one way of viewing black holes, which is to think that the sphere, the horizon, is small, and the inside is very, very long and narrow. It's like a tube. So a black hole, it's a small horizon with an immense volume inside. And as time goes on, going up this picture, time is growing, it becomes longer and longer and longer and narrower and narrower. And if you fall in, you don't get to the bottom. This is a girl falling in. You fall until the tube shrinks on yourself. And when it shrinks a lot, you enter the quantum gravity region. And what loop quantum gravity predicts is at that point, the tube cannot shrink more because you get to the granularity of space. So you cannot get smaller than that. And what does it do? It quantum jumps to something else. So at some point in time, the black hole, this long tube inside, quantum jumps to something else. Well, to what? Well, intuitively, it's not hard to guess what it could jump into because this is gravity, right? Things fall into black hole. The black hole itself is falling, right? Black holes are formed by stars which stop burning and fall onto themselves by their own weight. And so they open this hole in space and they fall inside. Now, when you fall, suppose you think at the ball that falls, if it cannot fall anymore, what does it do? Well, it bounces up. And bouncing is a sort of coming back. And that's what loop quantum gravity suggests happen. As time passes, the black hole gets to this quantum region, it bounces through a quantum jump, and then it comes back and becomes the time reversal of black hole. Like a ball that is bouncing up is a time reversal ball that is falling down, and it's called a white hole. So this is the prediction of the theory. From the black hole gets to a minimum size and then it bounces to become a white hole. The surface, the horizon, in the meanwhile becomes very, very small. So the white holes have a very, very teeny, very, very small horizon, but a huge inside, which slowly, slowly, slowly come out, releasing whatever information stuff was there. And some calculation, including some very recent calculation, indicate that the duration of this later phase, it's very, very long. For the technical experts, since Relian is in the audience, it's probably, according to last calculation, the mass to the fifth power. So it's an enormously long time, much longer than the evaporation time of the black hole. Well, let me say one, before I'm getting close to the conclusion, let me say one aspect of this story, which is perhaps the most fascinating at all. I said that the entire process takes a very, very long time, but careful. This is a long time of somebody staying outside and watching this to happen. So if you watch a star to collapse, forming a black hole, it takes a huge amount of time to become small. Then there's a quantum transition into a white hole and a huge time to evaporate. It's enormous time. But suppose you fall in, as I was describing this picture. You fall into the black hole, you go in, you go to this quantum region, you go through, well, you will be squeezed and killed, but suppose you will not be squeezed and killed. You continue the other side and then you come up later on. The time it takes that is very different. In fact, it's much smaller. Because one of the great discoveries of Einstein is that gravity changes the rate at which time passes. So in fact, if you go in, the time is very short. If you jump in the black hole and come out, it's a very short time passed for you, while your brother outside, who has been waiting for you, has been waiting a very long time. And the difference is colossal. For a black hole, for a certain size of black hole, you can compute, you can jump in and come out in a few minutes, while outside is billions of years. This is incredible flexibility of time. That's Einstein theory. That's believable physics. That's things we know about the universe can be tested in laboratory this kind of effects, not for black holes, but this time difference of rate of time in different regions. All right. So suppose this story is true, and the story, so this application of loop quantum gravity to black holes, tell us that on the black holes can be can evaporate, can become very small, they become very, very teeny things, and then they live for extremely long time. How could we test that? Well, when the universe was very hot and dense long ago, or maybe even before, it's very likely that a lot of black holes were produced, including teeny ones. Teeny ones that might have already gone through this process. So there might be around a lot of white holes, very, very teeny, living long time. And how would we see these things if there were a lot of these? Well, we would see these things as a sort of powder all over the universe, if there are many of them, which has a mass. So it interacts with gravitationally with the rest of the stuff, but has no charge. So it's not electromagnetic reactive. So we don't see that. Because to see something, there should be some electrons, some charges there that interacts with light. So there will be some matter all over the universe, which is dark. And remember that I said that astronomers, one of the open mysteries of the universe is that astronomers see a huge amount of matter, in fact, enormous amount of matter, more matter than galaxies, which is not made by electrons, atoms, protons, is not made by neutrinos, is not made by the stuff we know from the Standard Model, and we don't know what it is. So if this story is correct, it might be that dark matter, it's exactly this teeny remnants of black holes. I'm giving a simplified version of all the story. There is a lot of mathematics, there are a lot of details, but the core of the story is this one. So loop quantum gravity gives a possible answer of what happened inside the black hole, which we didn't know, what happened at the end of the evaporation, which we didn't know, but also of what could be the nature of this mysterious dark matter, which we don't know what it is. And many hypotheses out there, none particularly convincing. So here is another possibility, that there are teeny, teeny remnants of black holes that have evaporated. Can this be checked concretely? Can we make an actual measurement to check it? Well, yes, because loop quantum gravity tells us exactly the size of these remnants. Remember that I told you that a specific, the most characteristic aspect of quantum mechanics is discreteness, is the photons, the atomic levels, this quantities which are continuous. If we disregard quantum, they're not continuous, they are just specific values quantum mechanically. And quantum gravity allows to do the calculations of this discreteness of the quantum space. And the teeny remnant of black holes are inside an area. An area is quantized, and loop quantum gravity gives you the size of the quantization of the area. So the minimal area, the minimal non-zero area on which the remnant is sitting. Given what we know about black holes, if you know the area, you know the mass. So you know the mass of the grains of dark matter, if this theory is correct. And you do the calculation, it's very simple. It's of the order of a fraction of a microgram. So if the theory is correct, dark matter is made by a powder with that particular mass there. Well, it turns out that it's not too impossible using some quantum technology to measure these little teeny grains, these 20 micrograms. They're not particles; they're much more larger than elementary physics, particle physics particle. It's huge compared to an electron or a proton, but it's small, of course, compared to a planet or a grain of sand. 20 micrograms is the weight of my hair, okay? Imagine my hair, but smaller, more compressed, flying by, and it seemed to be possible to build detectors. There are some very recent papers on that, not with current technology, but with technology which is not too far in the future, to measure these hypothetical or predicted particles, which are remnants of evaporated black holes generated more than 13 billion years ago, floating around that could be dark matter. And since we know how much dark matter there is in the universe, if dark matter is this stuff, we know how many of these things fly. So we can estimate how big should be a detector to have a chance to capture these things. So I sort of close with a sort of reminding everything, and with my hope. We have basic theories of the universe that work very well. The holes, things we don't understand. Crucial thing we don't understand is the quantum property of gravity. That's for sure something we don't understand. Other things might be just we're not good enough to do calculations, or we're missing some details. Here we're missing something crucial. We need a quantum theory of gravity, a possible, not the only one, but possible theory of quantum gravity is loop quantum gravity. It predicts that black holes can evaporate and become small teeny things, which might be the constituent of dark matter, and might be, if this is so, detectable in the laboratory. And I close the way I started. My hope is that before I die, or even after I die, somebody will be able to build this detector, measure these things, confirm the theory, confirm the discreteness of the geometry, the discretization of the geometry, the quantum space, confirm loop quantum gravity, and understand finally what happened to black holes, what is a quantum aspect of geometry, and what is dark matter. And my strong wish is that it's going to be a young woman from Gaza that has studied in a university in Gaza, doing that in a free Palestine of the future. Thank you.
Thank you very much, Carlo. I will first of all let you know that unfortunately, Dr. Ayman, the president of Al-Aqsa, who was there earlier, but there was a small technical issue. He wrote in the chat apologizing. Well, I let us apologize for this technical issue, but he thanks everyone. And Dr. Ayman, I'm not sure if you can still hear us, but thanks again, and we will definitely have you next time. Thank you so much, Carlo. I will now let Pierre, who is our resident scientist who understood everything you said, take over, and everyone can ask questions. Voilà, so everyone can ask questions, and Dr. Rovelli will answer them.
Okay, so thank you very much, Carlo. I think we could listen to you for hours. First, there are already a few questions, and I say if you want, there's a Q&A. You can write them directly here. First question, which is a bit more technical one, is whether or not you could give some intuition on why the evaporation time is like m to the fifth, and which computation it's based on.
Yeah. So for when this idea started to be developed, for long we all thought that the evaporation time of the remnant would be m to the fourth, which is much less, fourth power of the mass. M here is the mass, not of the remnant, is the mass of the initial black holes that has collapsed initially. The black hole is not that mass anymore; it's become very small. But the inside, the size of the inside still depends of how old the black hole was, and all the past history. So a black hole is not just determined by what happened in the horizon. The same horizon can have very different size inside. So a black hole that come from the evaporation of a big black hole has a much larger volume inside. So when it does a jump to the remnant, I call it white hole, but it's really more complicated than that. It's sort of quantum superposition of black and white hole. It's a white hole stabilized by quantum gravity phenomenon. And the reason m to the 4 was expected is because of conservation of information. All calculation go back to Pascal, was repeated in a number of ways. So the energy that if you start with a star, which is a big mass, so a lot of energy, it collapses, so the black hole has all this energy, this mass. But then when it evaporates, the Hawking radiation takes away the energy. It's like negative energy falls in, so it's like the energy comes out. So when the transition happens, there's very little energy. There's a Planck energy there. Most of the energy has been radiated with a Hawking radiation, but the information inside cannot go out because energy, in a sense, can come back in time because you have negative energy, but you don't have negative information. So the information is inside. The Hawking radiation is it's not pure, it's thermal. This is called the black hole information problem. The information is inside. So you need the remnant to live long enough to bring out the information. Now, so you have the remnant has little energy and lots of information. And there's no problem in that. Sometimes particle physicists bulk that. I mean, you cannot have little energy and a lot of information. Well, of course you do. For instance, very many photons, each with very, very, very teeny energy, can have as much as energy you want, a mass of information you want, but having a lot of photons, and overall little energy. But you need a large amount of space because the photons have to be low energy, so long wavelengths, and long period, low frequency. And that's what forces a long time. So in other words, if you have a teeny hole and you want to bring out a lot of information with a fixed amount of total energy, you need a long time. And that gives M4. So that's what everybody had in mind of M4, which, by the way, seemed to be a little bit too short because it created a problem in cosmology. I'm not going to that. But very recently, there is a paper by Pierre Martin Dussault, which came out and was discussed at the last conference in Vienna, in which he has argument for M5th. And this is a geometrical argument. Pierre tried in his thesis, in his work, to do an actual description of the Hawking radiation, the energy momentum tensor of the Hawking radiation, as is inside, outside, so do the full story. And in trying to fit this, he was just not, M4 was not working. And so the paper is out, is not published yet, but is on the archives. It's a few months ago, but it was largely discussed in the last conference. So I think a lot of people got convinced that m to the 5 is more reasonable. If you want the technical details, just look at the paper. Pierre Martin Dussault on the archives.
Okay. Next question. What role does philosophy play in advancing modern theoretical physics, especially in quantum gravity?
Can you repeat the first part of what you said?
So you work a lot on philosophy too, philosophy of
Yeah.
science and physics. What role does philosophy play in advancing theoretical physics, especially in quantum gravity?
Oh, very good question. I think that modern education tends to separate completely scientific education from philosophical information, from philosophical education. And that's a mistake because if you look in the past, a lot of major advances in science were very much influenced by philosophy, and the scientists I mean, science is a global collaboration, right? It's not just one person doing things. It's a collective things. We do science together. But when you look at the moment in which bringing many results together, some jump in understanding happened, like Darwin, like Einstein, like Newton, like Maxwell, like Boltzmann, like Heisenberg. So the moments in which somebody says, "Oh, I have a new idea, a different way of understanding things," all these people that I mentioned were very much knowledgeable of philosophy and were very much influenced by the philosophy that they were reading. Heisenberg was under the influence of positivism, um, and Mach, and so on, and that's what gave him. I sometimes say no scientist does anything unless the philosopher does him or her the permission to do that. So philosophy uh, has always been fundamental in the past for the advancement of science. Einstein was certainly the greatest scientist of the 20th century. He had read all three Kant major book, The Criticism, when he was 15. And he was very passionate about Spinoza, about Schopenhauer, about Hume. So he had all this philosophical in his philosophy in his mind, and that was crucial for him to liberate himself from the straitjacket of Newtonian thinking and invent something new. And the same is true for the birth of quantum mechanics. The people who invented quantum mechanics, Niels Bohr, Schrödinger, Heisenberg, they were full of philosophy in their head. Niels Bohr was under the influence of Kierkegaard. Schrödinger was reading the Upanishad, the Indian major philosophical ancient text. Heisenberg, his main paper on quantum mechanics is almost the start is almost a citation of a philosopher or of the philosophical writing of an intellectual, which is Ernst Mach. So you need philosophy. Why you need philosophy? Because science is not write an equation and then make a measurement and test it. You guess an equation and then make a measurement and test it. Science is a very different operation. Science is changing your mind thinking, your ways of viewing things. It's realizing that some way of thinking is wrong and say, oh, I mean, I've always been thinking that way. I've always thought that space is just Euclidean geometry. No, forget about that. So science very often is to liberate your mind from a prejudice. And that's what philosophy is very good about, because it is a critical thinking about your own prejudice. Not always. I mean, there's bad philosophy. Sometimes scientists are under the influence of bad philosophy. But the dialogue is very, very strong. It is in both ways, because best philosophy, whether it's Kant or Wittgenstein or Hume, whoever, the best philosophers have always been very much following the science of their time. And some of the best philosophy comes from reflecting. I mean, we have learned this about the world. What does it imply? What does it mean for our general philosophical questions? So I see science, especially fundamental physics, but not only, also, neuroscience or biology, as a continuous dialogue between philosophers. Everybody does his own job, of course. I mean, philosophers don't write equations, and scientists don't write philosophy articles. But the more they learn from one another, the better chance, historically, history tells us, the better chance there is to going ahead.
And do you think we also tend to lock ourselves in some philosophical viewpoints, and which prevents us from advancing physics or science or even philosophy itself?
You said if I think we lack of what?
We tend to lock ourselves in some point of view, or philosophical point of view.
Yes, I do think so. In various ways, both substantially and methodologically. For instance, the 20th century had an explosion of fantastic physics, right? Quantum mechanics and general relativity. Both quantum mechanics and general relativity were very much influenced explicitly by Ernst Mach philosophical writing. And what Ernst Mach essentially said was the following. He was saying, look, Newton physics work fantastically well. So Newtonian physics give us a picture of the world, which it's a sort of possible metaphysics of the world. And if you think about 18th century positivism, and there's space or particles and pulled and pushed by forces. It's a very simple and convincing metaphysics that underpin the science of the time. And Marx says, careful, the fact that science works with this metaphysics is not granting that metaphysics, right? So don't get locked into thinking we have understood that the world is exactly like that. No, we have understood that to some extent the world can be understood that in that way. But maybe if we look at it further, we have to get rid of this and allow for a different way of understanding the world. Today, I think we face the same problem. In doing loop quantum gravity, one of the things that happen in loop quantum gravity is that you don't have a time variable. Time, in some sense, emerges in some regimes and not in others. So many people say, oh, no, that's impossible because, a priori, philosophically, I need time I need a forward moving time to make sense of reality. That's wrong. That's being locked in a wrong philosophical assumption. A second example of wrong philosophy, I think it's in methodology. Scientists, even the scientists that say, I don't care about philosophy, they're really doing philosophy because they have a methodology and they're influenced by philosophers. Even those who say, I don't care about philosophy, they say, oh, science is this and that. They're just repeating what some philosopher has done. And in theoretical physics, many are just repeating a sort of not well understood version of Popper and Kuhn writings about science. And they think, following Popper and Kuhn, or not very good understanding of Popper and Kuhn, they think that to do science is to just guess some theories arbitrarily and then test them, rather than working on the open problems and on what we know about the universe. And I think that's a wrong methodology that has misled fundamental physics in the last decades. There's a reason of a certain sterility in fundamental physics. Everybody's guessing a new theory beyond general relativity, beyond quantum mechanics, beyond the standard model, and it's 40 years that Nobel Prizes are given for confirmation of quantum mechanics, for confirmation of general relativity, confirmation of the standard model, and denying, falsifying speculations about new things beyond quantum mechanics, new physics beyond the standard model, new physics beyond general relativity. So nature is telling us you're doing something wrong just by speculating widely on beyond. Don't do beyond. Just see what you know and build on what you know. So that's another reason for which I think philosophical assumption, metaphysical assumption, methodological assumption can be wrong. That's why you need a constant philosophical awareness and discussion with philosophers.
So continuing on that, why would you choose loop quantum gravity instead of you personally instead of alternatives?
Well, there are two kinds of alternatives on the table in the literature. Some alternatives are some just vague ideas, not very developed, maybe thrown out some time ago, maybe new, but they're not theories of quantum gravity. They're just hints of, well, that might happen like that. And those are not theories of quantum gravity. I think quantum gravity is one of the few, perhaps two, three, no more than that, actual theories of quantum gravity that have been developed, studied, applied to cosmology, to black holes, to other things. So again, I don't think one should take too seriously just arbitrary ideas thrown out when they don't work, they don't produce things. With respect to the main alternatives, I mean, a big part of the community comes from the world of string theory, which was more inspired by particle physics than by general relativity. I find it that the big difference, again, has to do with the kind of philosophy of science I was mentioning before. String theory way of thinking is, let's imagine there is a unified theory of everything, of all the forces. Let's imagine that there are more dimensions. Let's imagine there is supersymmetry. Let's imagine that there's a tower of all infinite number of fields, and blah, 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 blah. Okay, so it's a lot of let's imagine, a lot of guesswork, and then constructing big mathematical things which have problems. So you try to solve the problem of the mathematical thing, and you go to zoom around in the space of mathematics. Loop quantum gravity seems more convincing to me. You're asking about my own opinion, of course, because it's just let's take what we learned from general relativity seriously. Let's take what we learned from quantum mechanics seriously, and let's see if there's a way to make them together. And that seems to me the way best science has evolved in the past when we don't have new data.
So I think many people would like to learn more about loop quantum gravity, and I've seen a question whether you would recommend any literature on the subject.
Well, there are many books of different kinds. Some are more mathematical, some are more introductive. I might mention a couple of things. I have some online lectures. I gave a course of introduction of loop quantum gravity in France, in Marseille, a couple of years ago. And these are online. If you search, my name. It's not immediate to find, but if you search on the line, that's a way. Just following the lectures. The lectures are addressed to a student who has some basic physics and already knows quantum mechanics, already knows general relativity, but no more than that. So it just requires basic physics education. I have a couple of books. One is more recent, is very much introductory. Is called Introduction to it's called Covariant Loop Quantum Gravities, together with Francesca Vidotto, and it's that's also very introductory. It starts with examples and we build the theory, and it's very up to date. I have an older book. The title is Quantum Gravity. It's much more conceptual. It goes through why I think in time in this way, why I think in space in this way, what are the main philosophical questions, how to build, and it's less up to date because it was written in 2004, long ago. But if somebody wants to delve into so what's behind this way of thinking, that's another book. So I would mention these three things of mine.
Okay, I pasted the link to the videos in the chat if you want.
Oh, fabulous! Okay, thank you very much.
Yes. And speaking of which, is there an idea, a basic fundamental idea in loop quantum gravity, which is to you the most important, and from which everything else arises?
Oh, well, yeah, there is one idea. There is a couple of calculations. The idea is to backtrack from quantum field theory to quantum mechanics. So quantum field theory it's very successful, of course. The quantum electrodynamics, the standard model is super. But quantum field theory assumes that there is a fixed geometry, and so you can have fields all the way down to arbitrary small things. And so the key idea is just, well, let's not assume that, because the fixed geometry, it's a quantum gravitational field, so we don't know if it is. So let's just use, let's study general relativity as it is and quantum mechanics as it is, without a priori using the tools of quantum field theory, namely fields at a point. In general relativity, there are no fields at a point because of difference invariant, because of coordinate invariance. So one has to use more general tools. So this, if you want, not taking quantum field theory tools too seriously, it's a main idea. And once you do that, you can write quantum operators, Hilbert space, and do some calculations. And the two key calculations. One is that you can do standard calculation of eigenvalues of operators, like the eigenvalues of the harmonic energy of the harmonic oscillator, or the calculation that tells you that the photons, the energy is h times the frequency, or the energy atoms in the Schrödinger equation. You can do the same kind of calculation, and you find the discreteness of geometry. You find the discreteness of volume, the discreteness of area. And so that's confirmed that space-time is granular, the quantum space. That's a key technical result, in my opinion. The other technical result is what started the loop quantum gravity in the 80s, is that the Wheeler-DeWitt equation, which is the Schrödinger equation of gravity, if you want, the quantum equation of gravity, admits some very simple solutions, which are loops with intersections. So that again indicates that there is a natural simplification that happens when you forget the infinity small. There's no infinity small in loop quantum gravity. That's the key idea. I mean, you were saying, is there a central idea? Yes, the central idea is that there's no infinity small. Forget this idea that there's infinitely small. There's just as small as a Planck scale. Planck scale is 10 to the minus 33 centimeters. It's finite. Nothing smaller than that.
Okay. Coming back to black holes, what happens to time in a black hole?
Great question. In some sense, something very radical. In some sense, something not very radical. So we learned from Einstein, this has nothing to do with quantum gravity, that time slows down when you go near a mass. This is a fact. Okay, if you take two clocks, you make one higher, one lower. The lower one is near to the Earth, and it goes slower. The one upstairs goes faster. So if you or your brother, one stays at the sea level and one goes in the mountains, when you meet, if you are the same age, if this is your twin brother, when you meet, you don't have the same age anymore because the one in the mountains have aged more. Now, between the mountain and the sea, it's a very small difference, can be computed. I always give this in my exams in general relativity. I used to give a compute how much if you spend 50 years in the mountains with respect to your brother, you lived more than him when you meet again. And it's just a few milliseconds, so it's just nothing. But it's real, and it can be measured in the laboratory. So near a black hole, this phenomenon becomes much, much stronger, colossal. So time is horrendously contracted. That's what I said in the talk. If you even go in the black hole, you can jump in the black hole, wait a few minutes, come out, and you come out in the distant future. You come out a billion years later with respect to what to the outside. That's what we expect, and this is credible because just forgetting quantum, we know for sure that if you go near a black hole outside, and wait a little bit and come out, when you come out, you're younger than than those your friends. There is a famous movie, Interstellar, where this is a Hollywood movie. Where this is it's put into the plot of the movie. One of the advisors of the movie was Kip Thorne, who got the Nobel Prize for the gravitational wave detection. So it's a very reliable physicist, and it's the movie in this detail is very realistic. It's true. So this is main characters that goes near a black hole, then when it comes back, his daughter who was at the beginning of the movie. He's a man of middle age and has a daughter is a girl, and then at the end of the movie he meets again his daughter, and he's still a middle-aged man, but a couple of years older, but his daughter is an old woman. So the reason we're not used to that is just because we usually don't go near black holes. So in that sense, time is very distorted, and in the in the quantum jump from a black hole to a white hole, time is quantum. You can't even say exactly how much time it passes. It's a sort of quantum superposition of different times. Having said so, however, we're used to irreversible phenomena, time-oriented phenomena. Past is the past, the future is the future. And it's also true for a black hole. That doesn't change for a black hole. So the entire process is irreversible. So you can still think that is a good idea to describe it as evolution from the past to the future. And there's dissipation, there's entropy that goes up, and the standard time orientation of phenomena. That does not change.
Okay. And do white holes play a role in solving the information paradox?
Yes. I think that the information, there's no information paradox. Information go into the black hole and then may very well come out later through the remnant.
Okay. So I think I've seen also that a question whether there's a link. I can't find the question again, but whether there's a link between the bounce process of the black holes and the bounce process of the universe, if it exists in quantum gravity of
Yes,
the near the Big Bang.
great question. Yes, the answer is yes. With a caveat, it's a very similar phenomenon. Because I've not talked about that, but another main application of loop quantum gravity is try to understand what happened at the Big Bang. And many calculations seems to suggest, to indicate that a way of thinking at the Big Bang. So the Big Bang is, universe is very small and hot and compressed, and then it expands and it cools down and becomes very large. And that's credible. I mean, we're all convinced that this is what happened in the universe. Now the question is how did it started, or how did it get very compressed? And there are two possibilities which are the natural ones. One is that it was actually born like that. There was nothing before. It's possible. Nothing wrong a priori with that. it requires some intuition adjustment, but it's possible that sort of time itself was born there. But loop quantum gravity does not seem to favor that. It seems to favor the other possibility, which is that the reason the universe was so hot and compressed is because it got hot and compressed by falling into itself. A large universe full of matter and stuff and stars or whatever, black holes, I don't know, by gravity, by weight, sort of falling into itself, and then it got very, 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 very compressed. And again, if there's no quantum, it would just boom, disappear into nothing according to general relativity. But there's loop quantum gravity, so it's exactly happened the kind of things I was describing. So the theory predicts that it gets a maximal compression and then it bounces out. And so the idea is that maybe what we are seeing at the Big Bang is just the bouncing out of a previously compressing universe. What happened even before, we have no idea. Now, the mathematics and the physics of the bounce of the universe and the bounce inside the black hole are very similar. The caveat is only it's similar phenomena, similar physics, namely you cannot compress stuff too much because of quantum mechanics, but it's not the same thing. It's not exactly the same mathematics, and the geometry is different. A black hole is it's a long, narrow tube becoming very, very long and narrow, and then it bouncing back, reopening, while the universe is like a sphere, which is all compressing and bouncing. And more importantly, a black hole is an outside. The universe doesn't have an outside. There's no horizon which stays put while this happened. So there's a similarity, there's a similar reason, but they're two different phenomena.
Okay. Could it be possible to have signatures of these bounces in case of black holes, black to white holes, at a distance besides the remnants?
I don't know. In the early times, when they first started thinking about the bounce inside the hole, in the first models that we were studying, we were hoping that it comes together with a sort of explosion outside, and this could be seen. In fact, I have a paper with Aurélien studying these possibilities. It's not completely over, but I'm less convinced that that's the right model. It seems to me, because for that to happen, the bounce from black to white should happen when the black hole is large. If it happens when the black hole is the end of the evaporation, those signals that we're hoping will be emitted are much weaker. So the actual calculation we did loop quantum gravity in some sense were disappointing, because I was hoping computing the probability of jump from black to white, the probability would not be small for large black holes. But it turns out, and a posteriori, that's what quantum mechanics is. I mean, big stuff don't behave quantum mechanical. You have to wait for them to be small to behave quantum mechanical. So what the calculation seems to be saying is that in order to have probability for jump, you have to wait for the end of evaporation. So most of the energy, of the large amount of energy, which is black hole, has already been emitted with Hawking radiation. And so there's not much stuff emitted to observe. The models are evolving. We have studied the slow radiation emission of the remnants. That's very, very weak. So it's true there are many of these things, but it's still very weak. It's hard to imagine we can detect that one. Right now, it seemed to me that the best chance is to detect actually the remnant through its gravitational interaction. So we have an apparatus where one of these remnant is flying by. It has its Newton force. it's attracting thing. And you have some very delicate quantum interference technology to capture this little Newton force. That seems to me the most likely way of testing that. Having said so, we're in the middle of trying to figure this out. So I wouldn't exclude other ideas to come out or better understanding to come out.
Okay. So there are many questions, lots more that I could ask. So sorry if I miss some of them.
Yes, I think perhaps maybe one or two more questions, and then if that's okay with you, Carlo, so we don't take too much of your time. Just a few more questions. So Pierre, you're in charge of selecting the most pointed and interesting, and then we will wrap up and just say a few words or something.
Okay.
So just a few more questions. I think that will be good.
So a bit more general question, I guess. What advice would you give a young scientist on how to approach the uncertainty and complexity of the world?
The uncertainty and complexity of the world, or the uncertainty and complexity of becoming a scientist? The advice I would give, perhaps reluctantly, is to study a lot and not to jump immediately into doing one specific research line. It seems to me that current education everywhere makes a mistake of giving you some basic information and then say, okay, here is a problem, do a calculation, continue to develop this particular model. Seems to me that that's not how to become a good scientist. You have to take your time, study this, delay before plunging into. Perhaps I'm just talking about myself, but I finished my PhD without any paper published because I just studied. I studied everything that was on the literature at the time on quantum gravity. Maybe that's much harder in the current climate today. Pressure for publishing, for getting a postdoc by showing, oh, I have so papers, so I'm better than the others. No, it's not by having more papers that you're better than the other. Okay, you can be much better than the other with just one paper, and you have understood something. There's a sort of idea of doing science by routine, publish a paper. We can do this, we apply to that, so I can publish a paper. That's not science. That's self-reproducing of a useless thing. Science is step back, slow, think, understand, and say, this and that, maybe I can do something new, and then it doesn't work, and then you do something else. So it's a lot of trial and error in thinking. And for this, it takes time. So my advice, of course, is there's a balance between that and the pressure of the market to produce, but don't get too much absorbed in the pressure of the market. Give yourself the time to think, and don't be stressed. I mean, it's wonderful to be a scientist if you feel that you're producing something, and it's very hard to judge oneself. When you're young, you have no idea what you're good at, what kind of things you're good at. But try, and slowly it will clarify.
And also, you talked a lot, of course, about quantum gravity, cosmology, and so on. Is there a piece of physics or science in general that fascinates you, but you don't study?
Plenty. In fact, it's so sad. I mean, there's an Italian comic actor, well known in a movie. He has a famous line. He says, "Oh, this is not fair. There's so many of them writing. There's just me on reading. It's not fair. There are plenty of things I would like to learn. I would like to learn, I don't know, the chemistry of protein. One thing that is actually fashionable, but certainly I would love to know more. It's all the variety of study about the human brain, which is so much is being learned. I would like to learn all these things. Maybe that's one of the thing I would like to know more. But biology, basic biology, I mean, how the hell proteins, how work. It's great because in a sense we have worked out the main, there are no more great fundamental open question like it seemed before, right? So not long ago, 50 years, people were asking the question, what is life? And nobody's asking that question anymore. The question is, how does life works? But not what is life? Life is that thing, all this very complicated biochemistry, and I would like to know more about that.
Okay, thank you very much. I also didn't read the many dozens of thanks and congratulations and so on.
Okay, I think maybe we're going to wrap up. Hazem, can you hear me? If you're online.
And Christine, can I ask one thing to Pierre? Can you
Yes,
save?
of course.
Can you save the chat and the questions?
I think you can save the chat. The questions I
can do
don't
it
know.
myself. I would like to slowly then read them, and so people who wrote them.
I think so.
Thank you.
I'm quite challenged when it comes to technology, and
yes, it will.
I think
it will be
Yes.
saved automatic.
Okay, very super.
And we will get them and we will share them with you. Yeah.
So if it's Saida in charge, then you know everything's going to be okay.
Thank you.
If Hazem is here, I think he wanted to say a few words on behalf of the president of Al-Aqsa, Dr. Iman, who could not make it, but I think he has unfortunately left. So here he is. Maybe Hazem, can you hear us?
Yeah. Like just a minute, please. Just a minute, please. Just a minute, please. Can you hear me?
Yes, we can.
Yes.
We're very happy. Hazem is in Gaza now, and he's the Dean of the Faculty of Science at Al-Aqsa University. Hazem, so good to hear you, actually.
Okay. Greeting to all. I'm speaking to you from the destroyed university buildings. First of all, I would like to apologize for inability of the university president, Dr. Ayman Sobh, to participate due to an internet connection problem. Secondly, I would like to thank my dear Dr. Christine for her constant interest and coordination for this program of scientific lectures, which will continue for several months. Third, I thank Dr. Carlo for accepting to give the lecture through Al-Aqsa University website. This is a distinctive addition to our university. Our university has 12 faculties, including the Faculty of Science, which includes 4 departments: chemistry, physics, mathematics, and biology. The Faculty of Science is staffed by a group of professors with excellent H-indexes. Unfortunately, I'm sorry to say that we lost some of them in this genocide. Gaza equals genocide, which equals destructions, hunger, thirst, ignorance, and diseases. We will continue and challenge the difficult circumstances. My name is Hazem Abu Shawish, Professor of Analytical Chemistry and Dean of Scientific Research at the university. Thank you very much again.
Thank you so much, Hazem. And it's good that Al-Aqsa had its voice too in this webinar. There was an issue about translation. I apologize. I think we could not turn on the translation, the simultaneous translation during the webinar. But for the next webinar, hopefully we will sort it all out and we will all be much better at it. The next webinar will take place on 28th of May with Dr. Michel Brouet, who will talk to us about the local approaches to finite groups, if I'm not mistaken. You're all obviously very welcome. The webinar is recorded and will be made available. Here again, we'll just need to finalize the details. Thanks again to you, Carlo. Thanks again to Al-Aqsa. Thank you, Hazem, for making it in spite of the difficult internet connection and everything else that's difficult. And thank you to all the attendees and the panelists, because it's wonderful to be here. Saida or Carlo, if you want to add something before we say goodbye.
Goodbye.
Bye, Hazem.
Bye.
Nothing else from my side. All my thanks and my solidarity, and I very much hope we get out of these horrible moments.